An engineering map is not merely a static picture, it is a complex mathematical engine waiting to be queried. Looking at this course syllabus, Unit 4 outlines the core techniques of GIS data analysis, specifically spatial and attribute analysis. Spatial analysis involves constructing explanatory and predictive models to subject spatial data to rigorous statistical testing. The entire analytical process relies on examining the exact locations, physical boundaries, and relationships between different spatial features. By applying specific tools and operations, we take raw spatial primitives, points, lines, and polygons, and mathematically derive entirely new datasets. Simple cartography displays what is already known. Spatial analysis extracts secondary data that did not exist in the original inputs. To execute geoinformatics accurately, an engineer treats the map as a dynamic, interactive database. Every operation in vector geoprocessing is governed by the geometry-attribute duality. Every physical boundary drawn on the map canvas is permanently tethered to a specific row of data in an underlying table. Tools like clipping or intersecting do not exclusively alter the spatial shapes you see on the screen. These geometric transformations simultaneously force mathematical transformations within those hidden data structures. Executing these specific tools without strict adherence to precise projection mathematics or proper aggregation logic is a severe professional pitfall. A visually flawless map can easily harbor corrupt and invalid engineering data if the underlying processing mechanics are ignored. Phase 1 of these mechanics is map manipulation, dealing specifically with spatial extraction and aggregation. The clip tool retains the spatial extent of an input vector layer based solely on the boundaries of an overlay layer. Analysts use clip to isolate relevant local infrastructure networks from massive national datasets. The inverse of this extraction process is aggregating geometry. The dissolve tool combines multiple distinct geometries that share the same specific attribute value into one contiguous shape. But dissolve carries a severe risk regarding unaggregated data fields. If an analyst does not explicitly define how specific attributes should be handled during a dissolve, the software simply retains a random data artifact from the original datasets and applies it to the entire new area. Forcing map geometry together without dictating the corresponding attribute logic creates compelling yet entirely false secondary information. Phase 2 is proximity analysis, the core methodology for location-based engineering problems. Buffering calculates a precise area of interest, or AOI, by pushing outward a defined distance from a point, line, or polygon. An AOI is the specific geographic boundary designated for study. When multiple buffer zones overlap, they can be automatically combined using the dissolve operation to create one clean boundary. This leads to the most notorious trap in proximity analysis, the megabuffer anomaly. Distance tools lack an absolute scale. They inherit their measurement units directly from the layer's assigned coordinate reference system, or CRS. A CRS is a mathematical framework used to map locations on the Earth's surface as precise coordinates. The strict rule for buffering is that the layer must be projected in a metric coordinate system, such as Universal Transverse Mercator, or UTM. UTM divides the Earth into zones and measures physical distance in meters. If an analyst mistakenly buffers a layer projected in geographic degrees instead of meters, the software interprets an input of 100 as 100 degrees of latitude and longitude, ballooning the buffer across an entire continent. Spatial processing algorithms operate blindly. Without the correct mathematical foundation of a metric projection, proximity tools output planet-scaled errors. Phase 3 is overlay analysis, requiring a close look at the intersection tool. Intersection identifies where two distinct layers overlap and extracts only that shared common geometry. Unlike the clip tool, the specific order of the input and overlay layers does not affect the geometric shape, as intersection only extracts the shared physical space. Intersection allows analysts to keep only specific fields from both input layers, preventing unmanageable data tables. However, intersection triggers a critical error known as attribute invalidation for absolute values. When a large land area is sliced in half by a boundary line, the newly generated smaller polygon automatically retains the absolute population count of the original larger area. Attribute values referring to a feature's total area, volume, or raw count are rendered completely meaningless the moment the geometry is intersected. Slicing spatial features does not execute proportional math on their databases. The analyst must identify and recalculate these corrupted metrics manually. We can apply these mechanics to a practical workflow, calculating the historical loss of vital surface water. In this scenario, the analyst has no modern vector data, only an unreferenced historical map showing past lake boundaries. The first phase is digitization. We create a new dataset by tracing historical features into raw polygon boundaries. Next comes strict attribute management. We populate the new table with names, log null for unknowns, and assign status indicators giving the shapes mathematical meaning. The analysis culminates in utilizing precise geometric calculations to compare these historical boundaries against modern spatial data. The final actionable outcome is extracting the exact metric of how many square meters of surface water have been lost. This final engineering metric is legally and mathematically valid because the underlying projection was strictly metric and attribute inheritance was tightly controlled at every step. True spatial analysis is the simultaneous, rigorous engineering of both visual geography and tabular databases to uncover absolute physical truth.